I hope with a little more stress on the architecture of IoT systems. So this is going to be the very broad outline of my talk. We'll first look at IoT overview. Then we will see how IoT as is defined today differs from a slightly older paradigm. I won't call it a protocol, it's more like a paradigm. There's M2M or machine to machine. Okay, then we'll take a look at IoT architecture, IoT ecosystem, how it exists in a broader framework, then other standards, protocols, and platforms. So let's start. So obviously we start with what exactly is IoT. Now, as you must have realized from the previous talk and also from your existing knowledge, that IoT is very much a field which is in flux. What IoT means today is not what IoT had meant, say, 5 years back or 10 years back. And certainly the meaning is not going to stay static for very long. Maybe 5 years down the line, we'll look back and we'll like to redefine the entire concept of IoT. Or maybe IoT, the name itself will change and some other nomenclature will take over, a bit like putting old wine in new bottles. But still, what Internet of Things means today, it's a trend where a large number of embedded devices employ communication services offered by internet protocols. So things here basically are these devices. They are not persons. Basically, when devices are talking, maybe to persons, maybe to other devices, and to do so, they are using communication services offered by the internet protocol. So that is why Internet of Things. Often, these devices are called smart objects. In fact, a very simple layman's test to identifying what belongs to, say, IoT and what does not depends on whether or not we can add the word smart before it. For example, smartphone, smart city, smart this, smart that. So it means they're all using the concept of IoT to smarten themselves, basically. So another touchstone test would be whether or not they are directly operated by humans. Often human interaction is supposed to be, or direct manual intervention is supposed to be absent. Of course, it is not perfectly true. A lot of manual intervention could also happen, but it's not often done in real time. It is more like a monitoring kind of thing. And they exist in components like buildings, vehicles, or are spread out in the environment. They could exist all around us. So very much part of ubiquitous computing. And also another thing, another aspect which I would like to add to this is that these things are not necessarily static. They could also be mobile. They could be changing place. Now, let's see how the Oxford Dictionary, usually we take the Oxford Dictionary definitions as a sort of earmarked kind of thing. So how it defines Internet of Things. First of all, it's very clear that it is supposed to be a noun. The interconnection via the internet of computing devices embedded in everyday objects, enabling them to send and receive data. And that is also a rather good definition. Now, why is IoT so popular these days? And why is everybody talking about IoT? What exactly makes it popular? What exactly makes it so all-pervading? First of all, ubiquitous connectivity. IoT is touching all our lives because we are all connected to the internet. We really cannot escape from the internet anymore. And the internet has become so all-pervasive. So connecting to the network has become ubiquitous. It is low cost, high speed, and all pervasive network connectivity, which is making IoT possible. If this connectivity had not been there, IoT would not have really succeeded as a popular paradigm. And then the widespread adoption of IP-based networking makes IoT a necessity day by day. Now, one of the major reasons why internet by itself is so successful is because there has been standardization. More or less, even though the internet is not really administered by any central authority, most of the internet works on the standard set of protocols which everybody accepts, and that is the reason why internet succeeds. And IoT, as it stands, though IoT, the concept of IoT was first proposed in the ending years of the previous century, and it's now more than 20 years old, so 2 decades have passed, but still IoT is largely a non-standardized way of computing or a way of affecting our lives. It is the standards still do not exist, but of course one does not start with standards. The standards evolve over time. So IoT is very much a field which is in flux, which is evolving. The standards are only now beginning to get standardized, as you would say. And so internetworking, basically the strength of internetworking or the success that internet has seen is one of the prime reasons why it is being used now to produce a more all-pervading computing paradigm, which we call IoT. Now, Moore's law continues to deliver greater computing power at lower price points and lower power consumption. So that is very important. If the components that make up the internet or the IoT devices, these devices, if they had computing devices, if they had not come within our price range, within acceptable price range, they would still have been confined to a very niche clientele, and it would not be so ubiquitous. So prices coming down, power consumption coming down are one of the prime reasons why IoT is beginning to become all-pervasive. Manufacturing advances also allow this cutting-edge computing and communication technology to be incorporated into very small objects. Now, one important reason is this low power consumption. We have to stress, really, we cannot really stress enough about power consumption. If power consumption is not reduced, then all our devices, they will lose their acceptability, usability, because often these devices are deployed in places where the lifetime of the device is defined by how long the battery power will last. So minimized power consumption makes it successful. If power consumption is not reduced, nobody will want to use them and they will not last long. So low power consumption, low price points as far as the device costs are concerned, these are very, very important. So the reduced cost, the reduced size, because they can be incorporated into very small devices. This high computing power can be obtained from from very, very tiny devices, so tiny that often we cannot really see them with our naked eyes also. So these are some of the reasons why this ubiquitous computing has now become so ubiquitous. In fact, we do not even call them computers, we call them controllers, we call them embedded systems, but basically in some scale or the other, they are all computers in the devices which are all around us. And of course, all this computing, all this communication would not be useful unless the data that they are producing cannot be effectively used to produce information, and from information comes knowledge and then wisdom, as Sir has already stressed. So the rise of cloud computing. Cloud computing is a computing paradigm, but the main idea is analytics, the ability to analyze data using features of machine learning, using other computing paradigms. This is what gives us the power to utilize the data which is being produced by all these devices which are interconnected and which are appearing on the net. And because we are able to use the data, we can produce some useful information or produce some useful application out of it. So these are some of the reasons why IoT is successful, why IoT will be more successful in future, and why it is so popular and so all-pervading in our lives. But again, the point which we have to stress is that the picture is not all rosy. There are certainly issues with this all-pervading presence of computing and data production in our life. Okay, so what are the various challenges that we face in with the rise of IoT, and what are these issues and how they can be accessed? So these are the areas in which a lot of work is now um, going on. uh, None of these issues have been solved 100%, and there are lots of open problems in there. Some of these sir has already touched, like interoperability. Interoperability will usually happen when there is some common language which the various different standards speak, which various different protocols speak. Presently, there is no single protocol, and there are no standards. So interoperability is not impossible, but it is a slightly difficult problem. So as people realize the need for a common language, it is to be hoped that the standardization will take place and interoperability will increase. Then privacy and security, they really cannot be stressed enough. It is very, very important, and privacy and security have always been an issue right from the time when we as students started working on single standalone PCs, etc. But as with time, these systems, the computing systems, have become more distributed. They have sort of spread out in space and time. So security issues have also become more and more complex. So we have seen how security aspects, uh, new kinds of attack modes, etc., turn up with increase in technology, with increase in availability of technology. Now, from distributed systems of computing devices or connected computers, we now have distributed systems which have things which are talking, which are not even humans. So lots of security holes open up, and these holes have to be identified and they have to be plugged. In addition, the issues of privacy have to be addressed, where how much data it is possible for government authorities, etc., to use, and how much data we would like to keep private, we would like to keep in our control. So these issues also touch upon legal, regulatory mechanisms, and also the rights of individuals. So these are some issues which are uh, being debated these days, and there are no fixed solutions, and also these are evolving pictures. Then we have the concept of emerging economies and development, how IoT uh, is a product of development, and how IoT is a catalyst in the development process. These are things which have to be very much addressed. And also, in the economies which are only now emerging onto the uh, computing scene, where like internet access is slowly penetrating, it is not really existing already. In such cases, how IoT can become a factor in the let's say the deeper penetration of internet into our lives, into the computing paradigms into our lives. So these are issues which have to be challenged, and how inequalities can be addressed where economic differences exist. So these are also issues which will touch upon this entire concept of IoT addressing our lives. Now, I told you before that we'll be discussing slightly on an older version of what is called IoT today, that is M2M, which is machine-to-machine communication. So machine-to-machine is a direct communication between devices using any communication channel, including wired and wireless. Machine-to-machine communication can include industrial instrumentation, enabling a sensor, meter, or meter to communicate the information it records to application software that can use it. So if you look at this definition, it sounds like the definition of IoT, what we have just encountered. So where exactly is the difference? The difference is machine-to-machine is for a particular application, Okay, when and actually machine to machine, or M2M as it's called, is an older protocol. You can say it is a smaller version of IoT. IoT has become a bigger umbrella version which does incorporate machine to machine. Now machine to machine is talks about mainly just 2 or 3 devices which are communicating, usually on a local communication system, not necessarily the internet. So IoT basically assumes that a more publicly acceptable, publicly available communication mechanism, which is the internet, is actually to be used. So Internet of Things, that's why it's called Internet of Things. It is not just communication between things. So machines are also things, but IoT has a slightly bigger perspective, has a bigger, wider application. So machine to machine, we can think of it as a narrow vertical. IoT is more like a horizontal picture. So why is IoT dominating? Why are people not talking about M2M anymore? So the disadvantages of M2M, these early M2M solutions are based on closed purpose custom built networks which did not necessarily agree or to existing standards. And often this custom built networks also had proprietary or industry specific standards. These industry specific standards were kept secret for industrial espionage reasons, etc. So you can think of it as an advantage as far as security and privacy are concerned, but then a big disadvantage is that you are not really making use of other available resources. So everything has its advantages and disadvantages. IoT is a more all-pervasive mechanism, but it has additional security issues, etc. So open M2M solutions have also been proposed these days, which are usually vertically centric, which means it serves a particular domain. So M2M has not gone away. It is very much existing, and it is also part of the wider IoT picture. The concept of IoT is to build a horizontal layer that overlaps all domains, creating one big platform. So let's look at a difference. For example, here, this is actually a very common example which you can see in many places. Shown as this is a bracelet which measures stress, okay, and it communicates with a cell phone, which then maybe communicates to a laptop. So it can be part of telemedicine, but then it's a very closed application, and you can say it's a closed loop, and it identifies this. So this could be an example of an M2M system. But if you move the same application to IoT, then you not only communicate with such a closed system, but you take many other factors into account, and maybe come to a conclusion which takes, say, the commuting experience of the person into account, whether he has been through a traffic jam which is causing the stress to build up. Maybe home environment has been difficult because there have been various device failures which have led to stress build up, or weather environment and various work environments, whether he's working in a very polluted environment or not. So the very fact of identifying stress, you can add more knowledge to it, and you can come to a more holistic conclusion about this. And this is made possible because all these other devices also are connected to the internet, and they provide data which can be turned into information. So it is possible to take a look at a much bigger picture where IoT is concerned, particularly because IoT is so it's more pervasive. It is not a closed application. So let's look at this horizontal layer of IoT. This is one way of viewing IoT, which some authors prefer. Other authors have other ways of looking at IoT. I will try to discuss a few different views of the IoT architecture. So let's start with this. As I have stressed, and as Professor Mishra has also stressed before me, that IoT is not really standardized at the moment. The standards are only evolving. So the horizontal layer, you could look at it like this. So there's the application layer, the application enablement, and internet connectivity. And below this internet connectivity layer, let's say, of the protocol, there are all these various devices and all these various situations from the data is being produced and which are being communicated to the cloud. So this represents the cloud, and so it's people, vehicles, buildings, various other assets, like transportation of goods, etc. Then industrial situations, which are actually a mine of information regarding various obtained from sensors, etc. Okay, agriculture and other spaces, various different spaces can actually produce the flood of data which feeds all these learning mechanisms, or the feeds all the data analytic algorithms which produce the information that we require. So the applications would be in automotive transport. I would like to add traffic conditions also here. Then various other utilities, then smart city, which sir has spoken of in length, then agriculture. Agriculture is actually a huge untapped market for IoT, I would feel at the moment. Then healthcare, certainly. It is my personal feeling that the healthcare as we see it now, or as we accept it now, is due for a massive overhaul, and IoT is going to play a huge role in this huge overhaul of the health sector, which is going to be, which is really waiting for us in the next few years. So let's talk about IoT architecture. Now, IoT, the most basic architecture, in fact, the earliest proposed architecture of IoT is a three-layer architecture. Now, all of us, we are familiar with the layered architecture of network protocols. It is good to remember that there was a time in the initial stages of the development of the internet, in the 70s and 80s, when these standards were not really existing, and various small networks, they worked on their own protocols, and it was the standardization which really helped the internet to explode in the manner which it has done. And IoT is only now in the process of doing this explosion. It has not really arrived there yet. So the most basic architecture is a three-layer architecture. Just like network protocols, layered architectures are advantageous. These layers are the perception layer, the network layer, and the application layers. The perception layer is where we have these various different types of sensors which sense various physical phenomena and which gather information about the environment. So these sensors could range from temperature sensors, smoke detectors, various visual sensors, cameras, etc., to other industrial level sensors, etc. So they can be of various different types. And in fact, one of the most all-pervading sensor which we carry in our pockets is in the form of our mobile phones. Mobile phones are very, very powerful devices in IoT applications. And so these are some of the physical parameters, and these are basically the things in Internet of Things. So the physical parameters and identify other smart objects in the environment. And also I would like to stress here that these things here are not just sensors, they are also actuators. Actuators which bring about changes like switching on the fan or turning a knob to control temperature, etc. These actuators also are part of the things which make up IoT. So sensors sense, actuators actuate or do something like activate a device, control the level of activity, and so on and so forth, like dimming the light or switching it on, switching on the AC, changing the temperature of an AC. These are the actuators. The network layer is responsible for connection, for connecting to other smart things, network devices, and servers. The features are also used for transmitting and processing sensor data. So network layer is the connection layer where the connection is actually happening. Usually it will be using internet protocols, IP protocols. Okay. And finally, the application layer, which is responsible for making use of this data which has been collected by the perception layer, and which has been transmitted by the network layer. And these are application specific services. So making sense of the data, providing some service out of that data, that is the idea of the application layer. And it defines various applications in which the Internet of Things can be deployed, for example, in smart homes, smart cities, smart health, etc. So if we look at the three layers, this makes sense. These are the perception layer, which are sensors and actuators. You can see they are sensing the level of a fluid, the lightometer, how bright the light is, sound sensors, etc., etc. So these are various sensors and actuators which control the switches, etc. And then the network layer, which consists of all the various ways in which communication happens. And finally, the application layer, where data is analyzed, data is acted upon, data is stored. Usually it will be in the cloud. There can be various servers, various storage devices, various algorithms running, etc. in this layer. So this is a very, very fundamental, you can say one of the earliest way of looking at the IoT layers which are in existence: application, network, and perception layer. But as usually happens, when we find that particular layers are doing more work, they begin to be broken up into smaller layers. So more newer layered architectures of IoT have been proposed. Another very popularly used architecture, which is actually built over this three-layer architecture, is the five-layer architecture, which additionally includes processing and business layers. The five layers, therefore, now will be perception, transport, processing, application, and business layers. The perception layer, application layers remain the same. The functions of the other three layers are as follows. The transport layer now transfers the sensor data from perception layer to the processing layer, and vice versa through networks like wireless, 3G, LAN, Bluetooth, RFID, NFC, etc. These are various ways in which the processing or the interconnection could be done. The processing layer is also known as the middleware layer. So what was basically previously the network layer has now basically been broken up into the transport layer and the processing layer. So there is a certain amount of processing now happening in the network protocols also. This is now called the middleware layer, and it stores, analyzes, and processes huge amounts of data that come from the transport layer. So it can also manage to provide diverse set of services. So if the analysis is happening at a more lower layer, then the response time would be quicker. So when real-time responses are required, some of these responses can be managed in the network layer, which has now been broken up into two layers: the transport layer and the processing layer. So this is where the idea of fog computing and edge computing is beginning to appear. So a certain amount of processing is happening below the application layer itself. It employs many technologies such as databases, cloud computing, big data processing modules. These are also happening at the processing layer. And finally, there's a business layer, which is on top of the application layer, which manages IoT systems, provides various business models, okay, and profit models, etc. It also deals with it has to deal with legal issues, privacy issues, etc., etc., and data storage, and so many other issues are involved. So let's look at this structure now. Previously, it was just plain application layer, network layer, and perception layer. Now, network layer, as you can see, it's been broken up to two layers. One is the processing layer and the transport layer, and business layer has been added on top of application layer, which actually uses these applications to create business models. Perception layer remains the same, of course. The gamut of applications have increased a lot. So now let's look at cloud and fog-based architectures. What is this? Cloud computing and fog. Cloud computing, I'm sure all of us know. It is like there's a cloud why it is called cloud is because it basically hides the details of the actual computing servers or the storage areas where they are. So it's a cloud is like a sort of abstraction, and it is providing services. It provides services which can be of various types: computing services, storage services, and various other services. So it is, you can say, a distributed processing environment in which there is a lot of hiding of the location of the processing location of the processing system, location of the storage system, etc., and where the computation is happening. So that is the concept of cloud computing. In some system architectures, it is done in large centralized fashion, or it could be in a distributed fashion also. The cloud-centric architecture keeps cloud at the center, the applications above it, and the network of smart things below it. So that is you can say the cloud is like an abstraction layer. Applications will use the information produced or the analyzed data produced by this cloud, and the perception layer and the network layer will feed information into the cloud. So this cloud is in the center. This is the cloud computing structure. It gives its primacy is because of its great flexibility and scalability. Now please realize that this scalability, the term scalability refers to change of size, change in scale. It can be reduction, it can be increase. I do not think anybody is really concerned about reducing size. We are always interested in increasing the amount of computability available to us, the amount of storage available to us. Okay, and this scalability comes mainly because of the distributed nature of cloud. Because it's a distributed nature, you can always add on more storage systems, you can add on more computing systems, you can add on various different applications, etc., into the cloud and make it available through the cloud platform. So the cloud is actually a very distributed kind of computing and storage platform, which has a central look, a centralized look. Okay, so and it offers services such as core infrastructure, platform, software, storage, etc. Developers can provide the storage tools, software tools, data mining. So it is sort of a center where you can sell your business, you can sell your services, and people who need those services can buy them. So that is the idea of a cloud-centric architecture for IoT. And the fog-based architecture, I'll come to the diagram just a minute later. Let's just see what is this fog computing. Or maybe I should move ahead and see where. Okay, so this is the fog architecture. The cloud-based architecture we have already seen. Okay, and so this is the fog. Let's discuss fog-based architecture first. So this fog-based architecture is of more recent vintage, which says that the sensors and the network gateway do a part of the data processing and analytics. We do not put we do not give the raw data to the cloud, but a part of this data is actually worked upon. It is analyzed. It is some kind of computation is done on it at the lower level itself. So the way I would like to analyze it is that a fog is nothing but a cloud at a lower level. When the cloud comes down to ground level, we call it a fog. Okay, so what cloud was doing, all the computing, hiding all the nature of the computing, what kind of thing. So that has now percolated to the lower levels, and it is called fog computing. The main reason is if you transfer raw data, then it takes up a lot of network resource. It requires a lot of time, and if everything has to be done in a cloud, your response time also degrades. So to improve response time, now here some people also draw a very interesting parallel to our nervous system, the nervous system that exists in our body. Okay, so the cloud could be your brain, all the information coming through the sense organs, which are the sensors and the actuators, they are sent to the brain for processing, and the brain processes them and sends them back. So the big cloud is there inside that. That is the brain, the central processing system. But then when fast response is required, like in our reflex actions, okay, it is often the spinal cord, which is actually part of the network architecture, which is doing the processing and activating the actuators, so to say. So reflex actions, so that you can think of it as fog computing or edge computing. Often this fog computing and edge computing are used, the terms are used synonymously. So the sensors and the network gateways do a part of the data processing and analytics. A fog architecture presents a layered approach which inserts some amount of monitoring, pre-processing, storage, and security layers between the physical and transport layers. The monitoring layer will monitor the power resources, responses, and services. So this is part of fog computing, where a monitoring is happening. Monitoring itself means that there is some kind of computing going on. There is some kind of processing of the data obtained by the sensors, which is going on. So that means a certain amount of computing duty has been moved to a lower level. The pre-processing layer performs filtering, processing, and analytics of the sensor data, and the temporary storage is, of course, certainly required. Without that, data processing would not be possible. So data replication, distribution, and storage also has to be added. Finally, security. Wherever there is data which is being handled, security comes into the picture. The security layer performs encryption, decryption, ensures data integrity and privacy. Monitoring and pre-processing are done on the edge of the network before sending to the cloud. So this is the fog-based architecture, where a lot of processing is done at the lower levels before sending onto the cloud. This can help, for example, with privacy, where the fog, the computing at the lower level decides which data must be sent on, which must be kept at the local level. It can help with encryption, which also adds to security. It can help with reducing the network, the volume of the traffic in the network. So there are various advantages to having a fog computing architecture. But the challenges faced is that previously, one of the strengths of the previous architecture was that the sensors and the actuators, they were lightweight devices with not too much computing power to them. But if a certain amount of computing has to be done in the lower, in the device level itself, the device, they become a little more voluminous in terms of the functions they have to perform. So they are not really as lightweight as before. So this is the architecture of a fog computing system for a smart IoT gateway. Okay, so between the physical layer and the transport layer, you have all these, you can call them layers, you can call them functions, which are part of the fog computing. That is monitoring, pre-processing, storage, and security. So these are the aspects which have been introduced at the lower levels itself. So we can see how the very basic initially proposed 3-level architecture is now becoming more sophisticated. Okay, often the terms fog computing and edge computing are used interchangeably. Actually, edge computing was proposed earlier. Fog computing or fogging is what is used nowadays. Fog computing, originally termed by Cisco, refers to smart gateways and smart sensors, whereas edge computing is slightly more penetrative in nature. This paradigm envisages adding smart data processing capabilities to physical devices like motors, pumps, lights, etc. So the light itself monitors what the ambient light is and whether it should dim itself or whether it should switch itself off because maybe it is now daytime, and so on and so forth. The aim is to do as much of pre-processing of data as possible in these devices, which are termed to be at the edge of the network. So that is edge computing. In terms of system architecture, there is not too much difference between fog computing and edge computing. So yet another look at the layered architecture of IoT systems. This looks like the 3-level architecture, but you can see there is some additions to it. For example, the sensors, the things in IoT, Internet of Things, these are here, the sensors and actuators, which are IoT-enabled devices, mesh networks, etc. Okay, then we have the connections to the IoT gateways and routers. Okay, and these connections are usually on the basis of local networks like Bluetooth, Zigbee, RFID. It's a misprint here. It's RFID, NFC, etc. And then in the gateway level itself, there is a certain amount of computing happening. Okay, and from gateway to the cloud, you can of course connect through various other means. And in the gateway level itself, there is some computing, and this is you can say the domain of edge computing. Now, another layered proposal, which is again becoming quite popular, is the 7-layer architecture of an IoT system. So, IoT application architecture. This is not a particularly good picture, but still it gives us some idea. Let's just look at it. So you have first these physical devices. We are actually familiar with quite a few of them already. And then the connectivity of the physical devices to edge computing devices, which are doing the computing or some amount of processing or pre-processing of the data at the local level, then data accumulation, data abstraction, and finally application, reporting or analytical center. This you can say is the cloud, where we actually move to the cloud. And then collaboration and processes involving people, business process. So there is a certain amount of manual intervention. The idea of IoT is that this manual intervention should be minimized and it should be centralized. So manual intervention, if any, happens at the cloud layer. At the lower levels, there is no manual intervention. A slightly better picture, the same 7 layers. So layer 1 is the thing layer, okay, the devices layer, where you have the hardware devices, sensors, actuators, etc. Layer 2 is the connectivity layer, which has the network connectivity. This is the local connectivity to the local servers. And the fog computing, or here see edge and fog both are mentioned simultaneously. So edge computing or fog computing layer, where the data elements, analysis, and transformation is happening at the gateway layer itself. Then data accumulation, data preparation, data application, and finally collaboration processes. By this proposal, these application, data preparation, data accumulation, these are the 3 layers which are assumed to make up the IoT platform, which are supposed to make up the IoT platform. And these are where you have all these various IT-related tasks performed. And the lower levels are not really IT-related. All your algorithms, machine learning algorithms, data analytics, etc., happen in these IoT platform layer. And the lower levels do simpler data analysis, monitoring, filtering, etc., which come under the paradigm of edge computing. So we have seen first a 3-layer structure, we have seen a 5-layer structure, and we have also seen a 7-layer structure. So these layered structures are various different proposals. Another proposal here, this is a 4-layer structure now, but it has additional, let's say, blanket layers, which are the management layer and the security layer. Now, security being such an important factor, it really is going to make its presence felt or make its necessity felt in all the various layers of the application. Okay, so too many layers are also difficult to handle. So this 4-layer structure, what it does is it breaks into application layer, application support layer, the network layer, and the device layer. Now you can see it is just an extra layer over the 3-layer architecture that we saw before. Only security and management have been blanketed around all the layers together. So in the lowest layers, we have device capabilities and gateway capabilities. Okay, so the local connectivity or connection to the gateway is all bundled up into the device layer itself. The network layer basically talks about gateway to application or cloud connectivity. So network capabilities and transport capabilities come in this layer. In the application support layer, you have generic support capabilities and other specific support capabilities. And finally, the IoT applications layer is the topmost layer. Okay, and for security, again, these are security capabilities and management capabilities which are involved. So let's take a slightly more detailed view of these of this particular proposal of the layered architecture of IoT. So this is the lowest, that is device. So device capabilities, they sense and actuate. So sensors and actuators. So like sleeping and waking up of devices, of course. Then ad hoc networking. Ad hoc networking basically means that these devices are not necessarily fixed in place. They could move around, so the network topology could also keep changing. How the network is connected, the network between the things is also might also keep changing, and they might communicate directly or indirectly with the upper layers. They might communicate amongst themselves, or they might communicate through gateways. So we'll look at the various communication models in a few minutes. And then you have gateway capabilities, which are multiple interfaces support. That means they interface with various different devices, a number of devices. They can do some kind of protocol conversion, which we know are the various features of gateways, even in network systems. And also some kind of application logic execution environment. These execution would be what is called edge computing, and so on. Then this is the network capability, network layer, which connects from the gateways to the cloud. So you have these various network connectivity issues being handled at this stage. You can say all the various layers of the network protocol would be participating in this particular layer. Authentication, authorization, accounting, these are the various security aspects. Okay, and transport capabilities, so that the data and data reaches correctly to the correct place, and so on. Then we come to the application support layers. So the actual application, or the IT application, has now been again broken up into two layers. One is the supporting layer and the other is the actual application layer, because these IT applications have now increased in volume, complexity, and so on. So generic support, where data processing is done, data storage, where it is to be stored, how it is to be stored, that is decided. And the next is to provide support functions for specific applications. So these are the supportive activities of IoT capabilities, the IT portions. And finally, the IoT application layer, where IoT developers will be developing various algorithms. Often they'll be using data analytics, machine learning algorithms, etc., to devise or to execute programs which have been as required by the user. And management capabilities, the management layer, obviously all layers have to be managed. So these can start from device management, activation, deactivation, etc., firmware and software upgrades, network topology could be changed, congestion management, etc., which comes under your networking requirements, etc. So all these layers are sort of let's say managed by these management layers. So various management activities are performed by this management layer. So management activities which are involved with keeping all the various layers working smoothly, they have now been bundled into a separate vertical, let's say. And specific management capabilities, of course, for application specific necessities. And security layer, which is so vital and is required at every layer of the architecture. So this includes authorization, authentication, data confidentiality, integrity protection, privacy protection, all the things that we understand by security. And please remember, security impacts this IoT stack starting from device to application. Now, often when we think of security, we think of things like authentication, we think of cryptography, and network security, etc. But it is to be noted that security could also be in application. It could be in device layer. Even the devices have to be secure. So even the hardware devices must be secured with various security features. We should not have, for example, um, uh, counterfeit devices which have been introduced into the hardware and which are sort of compromising the security. So security has to be taken care of at every layer as required. Now, security and privacy concerns. This is something now which it is not only the researchers and the scientists who are thinking about, but every person who is even halfway knowledgeable about internet and the Internet of Things will start questioning data security, how safe my ID is going to be, how safe my data will be, etc. So security concerns have to be dealt with on a very plausible basis. So it is the biggest concern in adopting Internet of Things. So if Internet is entering my home, and through the internet the whole world is entering my home, where is my privacy? How safe I am from attackers who attack through the internet? Because all of us know now that attackers don't have to be physical attackers, they can attack through the cyberspace also. So how safe can I be? How secure can I be? So these are questions everybody on the ground is asking today. With concerns of rapid development, it is happening without appropriate consideration for the security challenges involved. And the regulatory mechanism is always a step behind and keep playing the game of catch up. So technical security concerns are similar to those of conventional servers, workstations, and smartphones, okay, which include weak authentication. If your authentication protocols are not strong enough, you can have impersonation happening. Forgetting to change default credentials, like using weak passwords, unencrypted messages sent between devices, and since transmission is not necessarily wired, even wired transmissions can be compromised, but when it is wireless, anybody can tap your conversation. Okay, so and these are various poor handling of security updates, etc. These are the various some of the reasons why security can be breached. However, many IoT devices have severe operational limitations, and since this IoT, the basic idea of IoT is connecting up devices which are small, lightweight, to make up a bigger picture, a bigger system which can deliver a bigger effort, which smaller devices on their own may not be able to do. So, but if we have to make all these devices secure, it means we have to, these devices are no longer lightweight. They have to have significant computing abilities, not only for edge computing, but also to ensure security. So these are contradictory requirements. To make IoT really pervasive, the devices have to be small, they have to be lightweight, they have to be cheap, they have to be easily available. But then if they have to be secure, if they have to do edge computing, they have to do fog computing, then they are not really light, small, cheap anymore. So some kind of contradictory requirements are in the picture, and as Sir had been stressing, it is the question of trade-offs, where you draw the line so that you have the best of both. So trade-offs are very important. That is where the engineering decisions have to be taken. So implementing firewalls using strong crypto systems, and consumer communicating with other devices at a low price. These are some of the requirements of things of the devices which have to be part of the IoT. So what are the main security objectives? If we this entire gamut of security requirements, if you have to make sense of them, we have to we have to define the context. So four important contexts. Please excuse me for a minute. So four main security objectives have been identified. So first is data confidentiality, where unauthorized parties should not have access to the data which is being transmitted and stored. Then data integrity. Nobody should be able to intentionally or unintentionally change the data which is being transmitted or stored. Then non-repudiation. That means if I have produced some data and people are working on it, and then someday when I am charged with the validity of the data, I say that I have not produced it, I am not the originator of this data, I should not be able to repudiate that. The sender cannot deny having sent a given message. So it is a bit like signing a document. When I sign a document, I stress that I am producing it, I have read it, and I verify it. I have verified it. So this is non-repudiation. And then data availability. That means sort of preventing denial of service attacks, where data should be available whenever required. Then IoT security and privacy concerns. Actually, these are some of the case studies of problems that have happened with IoT-based systems. Some of these are very, very common, and we are aware of them. Like internet-connected appliances could spy on people in their own homes, including televisions. Now, we are aware of some of these big issues, like with Huawei televisions, etc., and so on. And kitchen appliances, cameras in our TVs, hidden cameras which can switch on when the remote controller is switching on, and they can. And these have been used for spying. These are the stuff of spy stories, but they are very much a part of our lives these days with all-pervasive IoT. Thermostats, etc. It is not just that, it is also possible if you compromise IoT networks, for example, to use these compromised networks to actually stage attacks, not just cyber attacks like the banking systems, etc., but also attacks like, say, vehicle network. A vehicle could be controlled remotely. But please remember also things like pacemakers, insulin pumps, then implantable cardio defibrillators, etc. These are parts of various devices which are implanted into our bodies. Now, our bodies are also having various devices, and these are all IoT enabled often and can be calibrated from outside. The doctors often do the calibration of our, say, pacemakers, etc., from outside. So that means they are connected through the network, and suppose this network is compromised, these can actually turn into murder weapons in the hands of the enemies. So the possibilities are endless in which we could be put in danger because of safety or security breaches. And so poorly secured internet accessible devices can thus be subverted to attack others in various different, and this is just the tip of the iceberg, new and novel methods of attacking are at all times being devised. So it is very, very important to think of security and privacy issues and create trust if IoT really has to perform the role that it has been designed for performing. IoT has endless opportunities. The sky is the limit as far as the possibilities exist and how IoT can help us, but there are also difficulties on the path. These challenges which have to be identified and addressed in order to make sure that IoT is used in the proper way. But it does appear that the future lies with IoT. IoT is going to become more and more pervasive as days go on. Smart cities, smart villages, smart agriculture, smart healthcare, these are written in our future, as we all realize. And for these, it is up to us to ensure that the good systems are in place, good standards are in place, so that the benefits of IoT can be realized. I have few more slides on communication model. Okay, let's discuss communication models in small. I think I'm running short of time now. So in communication models which we have seen, you can often have device-to-device communication, for example, between the light bulb and light switch, which could be wireless, connected through wireless networks. Then you can have device-to-cloud model. It is also possible to have a device-to-gateway model, where the devices connect to a gateway, and the gateway itself is doing some kind of computing and might be giving orders. This is a part of, say, edge computing. And then the device and the gateway connects to the cloud. This is actually the popular three-layer model which we have been discussing. But it is worth noting that you can have even smaller layer models, where device to device is just one layer, device to cloud or application service provider, this is a two-layer model, this is the three-layer model, and so on. Okay, and even with the application service, this can be now broken up into parts. That is, the one is the application enabling service, the other is the application service provider. Okay, this is, so this if this part you can, if you expand it, this becomes the four-layer model. So these layers are also proposals. It is up to us to see, to watch and wait to see which is actually going to become the standard of the future. IoT ecosystems, I think I will not discuss today. I will stop here and maybe take a few questions. So if there are no questions,